Hi, my name is Miranda. I'm a PhD student of Doc Hensler. And so I will be talking about what comes before the photons today. Maybe can we make
change
this,
order.
yeah. Can we make this full screen maybe? Or
You know how to make this.
oh, I guess it is.
It was full screen.
Okay, whatever. It doesn't really matter.
That works.
All right. Okay, so in Gothenburg, we produce negative ions with cesium sputtering source. And so what happens is we start with some neutral cesium, and you heat it up, and it hits this ionizer, which has a voltage running through it. The cesium is ionized, but not 100% of the cesium. So the cesium that is not ionized coats the cathode, and this effectively reduces the work function so that we can produce a wider range of negative ions. And when this positive cesium sputters onto the cathode, it sputters out whatever material that is in the cathode that we want to study. And so we can accelerate this material out, and it can pick up those extra electrons that are floating around from the ionization process. So there are other methods of negative ion production, that being surface ionization and plasma. The problem with surface ionization is that the electron affinity of the material has to be larger than the work function of that material. And the work functions are quite high, around 2 to 3 eV. So if we want to study low electron affinity elements around 0.5 eV or lower, then we need to come up with a different way of production. And as for plasma source, same as cesium sputtering, it requires large samples. So if we want to study low yield radioactive elements, this is not possible. So we have to think of another way. And this can be accomplished with double charge exchange or electron capture reactions. So this is commonly done for neutralization and nuclear physics experiments. But if we continue to increase the temperature of the cell, then we can increase the cross-section of 2 electron captures. So here what we see is we can use a bunch of different targets, but this one happens to be alkali metal, specifically potassium. So we put solid potassium into a cell and we heat it up, and we continue to heat it up until that solid turns into a gas phase. And this projectile can be anything, but we had for this experiment that that you see a figure of now is for uranium-238. And so we have a projectile of positive uranium-238 that impinges on a target of potassium and gains 1 electron. So this energy defect will be positive. But if we want to continue on, the energy defect will become negative. So this is the difference between the electron affinity of the element, of the projectile element, and the ionization potential of the projectile. And so we have to figure out a way that we will minimize this energy defect here so we can optimize our negative ion production yield. And then, of course, there's a third reaction we have to consider, and this is if we continue to increase the pressure of the cell, we are also increasing the probability that we will have a third reaction and actually destroy our negative ions. As Dag mentioned previously, negative ions are quite delicate. And so this is experimental setup that we had at Isolde. And so first we started with a bunch beam of ions. And this is, again, the projectile that goes into a charge exchange cell and interacts with the potassium, gains electrons, and then we can measure these ions on a detector, namely a magnetop. And so this was our first result. So this you're seeing now is negative ion production of uranium-238 in a charge exchange cell. And so to our knowledge, this is the heaviest negative ion that has been produced in a charge exchange cell. And so we are doing this in hopes that we can produce heavy and radioactive elements so that we can then apply our photons and measure electron affinity values. And this was done at Isolde with the CRIS experiment. And so they usually probe hyperfine structures to extract nuclear values like electromagnetic moments and spin and changes in the mean square charge radii, and they're also investigating radioactive molecules. But now we're adding negative ions onto their roster. Okay, and so now how does this relate to RIGA? So with all this, there is a Gothenburg RIGA ion beam apparatus. And so here we can see an ion source with optics, electrostatic elements in the beam line that can guide these ions. And there's a charge exchange cell. So we plan to investigate this mechanism further here in Riga to understand this double charge exchange process that is going on. So we can hopefully make models and fit this data that we've had that you saw before. So like I mentioned, so we want to measure more negative ion production curves, and this will help us better understand predictions for negative ion production that we can then use at CERN to measure electron affinity values and isotope shifts. So thanks for your attention.
Okay, thank you.
Some acknowledgements.
Are there any questions? No, sir. Thank you. Then
Maybe you can comment, if you do experiments at CERN, what typical time cycle, what is a typical experiment in time? In hours, weeks? Yeah.
Oh, in hours or weeks. I mean, we're lucky to get a week of beam time per 2 years. So I am halfway in my PhD now, and I have yet to see I've had 2 days worth of experiments time. So this is a whole PhD cycle if you're lucky. Yeah.
So, I mean, that's motivation for
Studying
it here.
negative ion production in other places because the time is quite tight. So, yeah.
Hmm.
Thank you.
okay, thank you.